Hello everybody and welcome back. Welcome back to the 2005 Hypatia contest. That's the grade 11 level multiple choice contest. And here we are at question number 4, the very last question on the paper. An arrangement of a set is an ordering of all the numbers in the set, in which each number appears exactly once. For example, 213 and 231 are two of the possible arrangements of 1, 2, 3. So another name for arrangement is permutation. It might be something you've heard of, but this sort of falls under the general umbrella of combinatorics, which is generally removed from high school. High school nowadays is more about just getting everybody ready to take calculus. Most of high school can just be said, well, it's pre-calculus. Why do we do trigonometry? Because we need sine and cosine calculus. Why do we do the Cartesian plane and lines? Because we need to understand that for calculus. But there's fun other stuff in mathematics, and combinatorics is some of it, although you might not be as familiar with it. Alright. So let's get arrangement, permutation. These are fantastic things. There's 6 of them for 1, 2, and 3. So there's 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, which they have here, 3, 1, 2, another one that they have here, and 3, 2, 1. Those are the 6 arrangements of 1, 2, 3. So that's introducing us to the concept if we're not familiar with it. So we've got 3 parts here. A, determine the number of triples A, B, C, where A, B, and C are 3 different numbers chosen from 1, 2, 3, 4, 5, with A less than B and B greater than C. Explain how you got your answer. Alright, so this doesn't involve arrangements, because we're picking 3 of the numbers out, not all 5 to arrange them. I'm going to read a little further just to see where arrangements are coming in here. B, how many arrangements? Okay, it's in B. Of 1, 2, 3, 4, 5, 6 contain the digits 2, 5, 4 consecutively in that order. Explain how you got your answer. Alright. And 2, 5, 4, that's with 3 digits, and the middle one is the biggest of all 3. Okay. So I guess that's what they're building to. While we're at it, let's read C. Sometimes it's a good idea to read the whole question at once so you know where you're going. And we made it this far, so let's go read C. A local peak in an arrangement occurs when there is a sequence of 3 numbers in the arrangement for which the middle number is greater than both of its neighbors. For example, the arrangement 3, 5, 2, 4, 1 of 1, 2, 3, 4, 5 contains 2 local peaks, one at 5, one at 4. Determine with justification the average number of local peaks in all 40,320 possible arrangements of 1, 2, 3, 4, 5, 6, 7, 8. Okay. Interesting. Average number of local peaks. Alright, well, we'll build up to that. Let's just go back to A. Number of triples, A, B, C. So, B is the biggest number. I think it's probably wisest to choose B first and then see what do we have left that can be smaller. Okay. So we'll get rid of question 3 here and get a fresh piece of paper. Alright, so got A, B, C. Both A and C are less than B. And since A is not equal to C, we can see B must be at least 3. Because if it were 2, how can you have 2 different numbers smaller than it? So that's a pretty quick observation. What to do here? So out of 1, 2, 3, 4, 5, we see B can be 3, 4, or 5. So I think it's probably just going to be case-based. If it's 3, what numbers could we have for A and C? If it's 4, what numbers could we have for A and C? If it's 5, what numbers can we have for A and C? So if B is equal to 3, then A and C are chosen from the numbers that are less than B. So A is 1, C is 2, or A is 2, C is 1. Not particularly hard. If B is equal to 4, A and C are chosen from 1, 2, and 3. So I could list them all out, but let's start being a little more clever. Let's choose A first. We have 3 choices for A. A can be 1, 2, or 3. And then that leaves 2 choices for C, the other 2 numbers left over. Because there's no relationship between A and C, it's just they have to both be less than B. So, number of possibilities. With B is 4, we have 3 choices for A times 2 choices for C, 6. And here we had 2. And we could view the same sort of logic works up here. We've got 2 choices for A, 1 or 2, and then C, there's only 1 choice left over for it. Finally, if B is equal to 5, A and C are in 1, 2, 3, 4. 4 choices for A, 3 choices for C. So that gives us 12 different possibilities. And we could verify this to ourselves by writing them out. I don't think it's necessary. But if we wanted to, or as an alternate strategy, just to double check it for us, maybe we're one of those students who's not particularly strong, you've made it to 4, you've followed my advice, and you're trying for A. Do I understand basic definitions of whatever's going on? If you can get to 4A, and if you're willing to try it, and you say to yourself, well, I've read B and C, I don't understand what's going on, I don't think I can try them, then spend extra time polishing up the questions you've already done, and making sure that the 4A that you tried is correct, and 4A could be done just by writing everything out. So if you've got the time, you've made sure the other questions are fine, and you say to yourself, I can't do B and C, make 4A as good as possible, and write out all the cases. But as I say, I think we're fine. So there are 2 plus 6 plus 12, and that's going to give us 8 plus 12, so 20 possible A, B, C's. Okay. So A, B, and C are sort of like a local peak, which is what they were talking about in C part. We just don't have them written together like A, B, C. And as I already noted in B part, we sort of see how to move a given local peak around. Once the 2, 4, and 5 are chosen, we're all set. Other ways we could make these triples. I'm just trying to think of other ways to do part A. And I think if you choose any 3 of these, and then because you can order A and B or A and C around B, double that number would be fine. So if we know, so just before I move on from A part, another way to do it, if we know combinatorics. And as I said, not everyone knows combinatorics, so this case-based work is fine. But another way to do it is, for A, B, and C, we need A and C less than B. So for any 3 numbers in 1, 2, 3, 4, 5, so for any 3 numbers, maybe call them X, Y, and Z, we know that the biggest one, Z, has to be B. So we can make 2 such A, B's, and C's. B must be Z. And then either A is X, C is Y, or A is Y, C is X. There are 5 choose 3. This is if you know this notation. It's 5 factorial over 2 factorial times 3 factorial. And these are the number of ways to pick just 3 numbers. One, 2, 3, 4, and 5. And 5 choose 3, most calculators will do choose stuff, but this guy happens to also be 10. 120 over 2 over 6, so 120 over 12 is 10. So there's 2 for each of these, and there's 10 of these triples. So there's 20 A, B's, and C's that we could have. So that's another way to do A part. A little more combinatoricsy, but certainly a little shorter and less casework. But I think we're ready to move on from part A. So let's take a look at B part. So we'll read it again. How many arrangements of 1, 2, 3, 4, 5, 6 contain the digits 2, 5, 4 consecutively in that order? Explain how you got your answer. Alright, so we're basically, if 2, 5, and 4 are fixed, since 2, 5, 4 is fixed, what we can do is we can treat it as a single object to arrange with the other numbers, the ones that are left over, 1, 3, and 6. We then have 4 objects to arrange, or to order. Another name for permutations is orderings. Linear orderings specifically. There is something called circular orderings. We're not going to talk about it. We're doing a Hypatia. So we have 1, 3, 6, and then the 2, 4, 5 thing all together. And basically, to make an arrangement, we just have to order these guys. So we've got 4 places to put them. We have 4 choices for the first thing, times 3 choices. Once we remove, say, the 3, we're left with 1, 6, and the big thing. Choices for the next one, 2 choices for the remainder, and 1 final thing that will be left over once we've chosen the first, second, and third things. We multiply all these choices together, and we get 24. This is also known as 4 factorial, if you're familiar with it. 4 times 3 times 2 times 1, just like 5 factorial is 5 times 3, 4 times 3 times 2 times 1. Okay. So 4 choices for first object, 3 choices for the next, and 1 choice left over. So there are 24 different arrangements. 1, 2, 3, 4, 5, and 6. Having 2, 4, 5 somewhere in it in that order. So for example, using this, we could pick 6 first, then 1. We'd get 6, 1, then we'll pick the 2, 5, 4. So 6, 1, 2, 5, 4, and the 3 is left to go on the end. And that gives us 1 arrangement. There's 24 then. We made it this way, and we've explained what we're doing, where we make our choices, how to treat the objects. We treat it as a single fixed thing. And I imagine that'll help us with our local peaks, I think. So B part breezed by, but this is B is sort of an old style question. You see it a lot. You saw it a lot more when they did more combinatorics in high school, but you see it a ton in sort of first year university in a finite math course. All right, for C, a local peak in an arrangement occurs when there is a sequence of three numbers in an arrangement for which the middle number is greater than both of its neighbors. For example, the arrangement 3, 5, 2, 4, 1 contains two local peaks. Determine with justification the average number of local peaks in all 40,320 possible arrangements of 1, 2, 3, 4, 5, 6, 7, 8. Okay. So, first I'd like to speak a little bit about why it's 40,320 possible arrangements. Just really quickly, if we're arranging a set of numbers, our 8 numbers here, we've got 8 choices for the first digit. It could be 1, 2, 3, 4, 5, 6, 7, 8. Suppose it's 5. Well, then we take out the 5, we're left with 7 options for the next one, then 6, then 5, then 4, then 3, then 2, then 1. Since these choices don't exclude one another, we multiply them all together, and we get what you might be familiar with as 8 factorial. N factorial, just n times n minus 1 times n minus 2, all the way down to times 3 times 2 times 1. And 8 factorial, you can work it out on your calculator, and most calculators have a factorial button, is 40,320. So we got 8 factorial here. So there are 8 factorial in total arrangements. So why is this relevant? Why is it necessary to make this connection? Well, I don't necessarily know whether or not we need the 8 factorial. But as I've started segueing a little bit, as we did at the end of Part A, into doing some combinatorics notation, I thought there it is. But what do we want? We want average number of local peaks. Okay? How do we calculate average? Well, we need the total number of local peaks in all arrangements over the number of arrangements. So we're going to want some number over 8 factorial. So it's important to know where 40,320 comes from. Now, how do we go about getting the total number of local peaks? So I'll share with you guys the way that I did it in high school, or at least attempted to. I can't remember if I actually got this question. I think I did well in Hypatia this year, but I don't actually remember specifically. I remember the question because of the local peaks. And I remember my method here. But so what I essentially did is this. I said, well, what can we have? We can have one local peak. We can have no local peaks. And what does that look like? That looks like, something like 1, 2, 3, 4, 5, 6, 7, 8. That's no local peaks. You can have exactly one local peak. Just swap the 8 and the 7 around would do. But you can also get interesting other things. Like, for example, we see here, we can have 2 local peaks, and these ones are sort of smushed together. There's 2 options when it comes to local peaks. We can have 2 peaks together, and that requires 5 things. So you could have something like 8, 7, and then 6, 5, 4, and then 3, 2, 1, no other extra peaks. And so this would be 2 peaks together, or you could have 2 peaks separate. So something like 1, 3, 2, 4, 5, and then you could have 6, 8, 7. So that's 2 separate. Or you can do crafty things. You can't have 3 of them all separate because that would require 9 numbers. But you could have 2 together and 1 separate. And so that would be something like 2 peaks together, which would be 6, 8, 5, 7, 4. But the last 3 here get arranged into a peak. So 1, 3, 2. Or you could have all 3 peaks together. And so this is what I remember doing this sort of work. I can't remember if I abandoned it and did something else. But you could have all 3 of your peaks together, so you could have something like 8, 7, 6, and then 5, 4, 3, 2, and put 1 down here at the end. And so what I tried to do is I sort of figured out how many ways can we get one local peak, and then 2 local peaks together, 2 separate, and then there's sort of a very complicated Venn diagram sort of stuff. I didn't make a Venn diagram, but Venn diagrams are the best way to explain it. It's the principle of inclusion and exclusion. And so that's what I tried, and I can already see that trying to repeat whatever it was that was going through my head back then is going to be a bit of a nightmare. So I think there's a quicker way to do this. I'm just going to consider, instead of how many local peaks per arrangement, I'm just going to take a local peak. And I know how to create a local peak. We did that in A part. So instead of doing what I was doing, which it was a bunch of casework, so consider a local peak, like A, B, C, just like we have at in A part. So I'll figure out the number of local peaks, but consider a local peak, a given one. And we might ask ourselves, where can it occur? Or a better question, for this specific local peak, how many arrangements does it appear in? So rather than going arrangement by arrangement and counting up how many local peaks in each, which was what Young Root Beer tried to do with this, we could say, okay, give me a local peak. What number of arrangements does it occur in? And then there's still going to be overlap with local peaks, but there's not going to be overlap as to what arrangements this peak can occur in. You know, if this peak can only occur in 60, that's fine. 60 is what we've got. Well, how do we know how many arrangements something can occur in? That's B part. That's B part. So what we do is we consider A, B, C all together. And the other 5 numbers, because we took 3 numbers out to make this. We'll talk about how many local peaks A, B, C there are. And the other 5 numbers. And we're just going to arrange them. So this is an arrangement of sort of 6 objects. Now, if you know factorials, then you know it's 6 factorial. Or you could say, well, there's 6 choices for the first object, 5 for the next, and so on. You know, just like we have the 8, 7, 6, 5, 4, 3, 2, 1, giving us 40,320. So a given peak occurs in 6 factorial arrangements. Or if you wanted to calculate that out, it's 720. Okay? I'm going to keep it with factorial notations. Yeah. So a given peak. So now our thoughts turn to how many peaks are there? How many local peaks can we make? How many? What do we do with this ABC? And I already sort of spoke to that. I spoke to it in 2 different ways. You know, we can pick a B and then try and how many choices do we have for the A and the C. Or we can use my second, more combinatorial technique. Either one will do fine. If you do the first one with 8 numbers, it's going to be a bit of work because you're going to have B could be 3. How many possibilities? B can be 4. How many possibilities? 5. How many possibilities? But so I'm gonna do it the more combinatorial way. Pick X less than Y less than Z. So there's 8, choose 3. We have 8 numbers, we're choosing 3 of them. Ways to do this. And of course, this is 8 factorial over 3 factorial, 5 factorial, for those of you who don't remember your binomial notation. B has to be Z, or Z has to go B. It's got to be the big one in the peak. And then we've got 2 choices, either XZY or YZX. So there are 2 times 8 choose 3 different peaks, each one appearing in 6 factorial arrangements. Okay, and yeah, they can overlap, and you can have, you know, the 2, 3, 1 peak here, and you can have the 1, 5, 4 peak, and they can overlap. Doesn't matter. We're still counting the number of peaks, and this gets around any inclusion-exclusion stuff. So the total number of peaks, which is something we need to get the average number, is, and now we can calculate it, it's the number of different peaks times the number of arrangements each peak appears in. So 6 factorial. So we get 2 times, we can do 8 factorial over 3 factorial, 5 factorial, 6 factorial. But 6 factorial is 6 times 5 factorial. So we get 2 times 8 factorial over 3 factorial times 6. 6 and 3 factorial, the 3 factorial is 6. So we get 2 times 8 factorial, and that's as simple as we need it. So now the average number of local peaks is the total number over the number of arrangements, which I already said is 8 factorial. So it's 2 times 8 factorial over 8 factorial, or just 2. And if you didn't want to do this with factorials, again, you could do a little bit of casework to figure out the number of peaks, and you'd get actual numbers. How many actual numbers of peaks are there? We get 876 over 6, so we get 8 times 7, 56 times 2. So it'd be 112 different peaks you would get, and so you'd put that in somewhere. And 6 factorial, again, you can have 720. So 112 times 720 over 40,320, all doable by calculator. Okay, so you don't have to worry about this factorial notation here. But the average number is 2, and that's a lot cleaner than whatever the heck I did when I first wrote this contest. So you do gain some wisdom and some insight as you get older with these things, but there it is. So maybe the next time you're doing a question like this in the future, on a future Hypatia or future Euclid, you'll think, you know, should we be counting the number of peaks or the number of arrangements based on their number of peaks, that sort of thing. And you might think back to this, and you might choose the better of the two methods. Okay. But that does it for the 2005 Hypatia. Thank you so much for watching, and I'll be starting the Euclid shortly. So we'll look forward to that, because it's more written stuff, more practice for our proofwriting, and that's what we need to do. Okay, so have yourselves a wonderful day.